Okay, so let's continue previous class. That means numerical. We already find the efficiency ohmic loss at maximum efficiency. That means n square into 80 watts equal to 50. So n equal to square root of 50 divided by 80 equal to 0.79. Okay, at this fraction of load, you will get the maximum efficiency. Okay, so kVA output at the maximum efficiency is equal to n into kVA rating of the full load. Okay, so kVA output at the maximum efficiency is equal to output at maximum efficiency maximum efficiency, that is eta maximum equal to n into kVA at rated full load. Okay, or full load. And out here eta maximum equal to n into kVA at full load. Okay, so n times kVA at full load kVA at full load or rated load. Rated load. Okay, so n equal to 0.79 into 10 what into 10, that is equal to 7.9. Okay, 7.9 kVA at the maximum efficiency. Note that kVA output at maximum efficiency, kVA output at maximum efficiency not depends on the load power factor. Okay. Does not depends on load power factor. Load power factor. Yeah. So for maximum efficiency, ohmic loss equal to, what is the condition? Ohmic loss equal to core loss. Okay. For maximum efficiency, when the ohmic loss is equal to the core loss. Maximum efficiency that means ohmic loss equal to core loss. Equal to core loss, that means 50 watt So and the total loss at maximum efficiency equal to how much? Total loss at maximum efficiency can say equal to 50 plus 50 is 100 watt. The magnitude of maximum efficiency equal to the magnitude of maximum efficiency means eta maximum equal to just write here eta in suffix maximum, okay, equal to 1 minus losses divided by output plus losses. So 1 minus total losses is your 100 watt. Okay, 100 watt. And output power at maximum efficiency equal to 79 kVA. That means 7900 7.9 sorry 7.9 kVA. You convert in volt ampere. That means 7900 into power factor. That means 0.8. 0.8 plus total losses 100. So maximum efficiency equal to 98.44%. 98.44%. Okay. So this is your efficiency of maximum. Now, if we try to solve the part C, okay, in part C, that is voltage regulation and the secondary terminal voltage at the 0.8 power factor lagging and leading. Is it not? So this is your part C. Calculate the voltage regulation and secondary terminal voltage under the 0.8 power factor lagging and 0.8 power factor leading. So just wait here. Problem programming. Now, if you try to solve the problem part C, then how we can approach this problem? Suppose that from the data of short circuit, you can find the equivalent resistance of on the high voltage side and reactance on the high voltage side. So just try to find out from the data of short circuit test. Okay. Short circuit test. REH equal to power divided by current square. Okay, you can write here equivalent resistance along the high voltage side. So REH equal to power divided by current square. So power is given to you 45 and current is 3. So 3 into 3, that means 9. Okay. So resistance is equal to 5 ohm. Is that 5 ohm? Similarly, you can find the leakage equivalent leakage reactance along the high voltage side. That means XEH. XEH equal to how much? Voltage divided by current. Is it not? XEH equal to voltage given to you how much? 60 watt. 60 volt, sorry. So 60 volt divided by current 3. 60 divided by 3 equal to 20 ohm. Equal to 20 ohm. Okay. So now you can find the value of impedance. Sorry, this one is JDH. JDH, that means impedance, equivalent impedance along the high voltage side. Now you just find out the equivalent leakage reactance along the high voltage side. Okay. So XEH equal to the square root of JDH square minus REH square. JDH square minus REH square minus REH square. Now you just put here the value of JDH and REH. Okay. So So square root of JDH, that means 20 ka whole square, that means 400 minus 5 ka square, that means 25. Okay. So if you solve this equation, you will get the value of XEH equal to 19.35. Okay. So now find the equivalent resistance in per unit. Okay, that means epsilon R and epsilon X. So per unit resistance and per unit leakage reactance. Per unit resistance is represented by epsilon R, epsilon R epsilon R, this one, per unit equivalent resistance in per unit epsilon R equal to IH REH divided by VH. So IH into REH divided by VH. Just put here the value of IH you already find out in the previous equation. So IH equal to how much? 4. So 4 into 5 4 into 5 divided by 2500. Is not 2500 equal to 0.008 0.008 per unit. Similarly, XEH equal to IH XEH divided by VH. XEH equal to IH XEH divided by VH. IH REH, sorry, XEH X H divided by VH. Okay. So if you put here again the value of IH XEH and VH, so IH equal to 4 into XEH equal to how much? 20. Sorry, 19.35 into 19.35 divided by 2500 equal to how much when you solve this equation? 0.031 0.031 in per unit. Okay. Per unit. Per unit. Okay. Now voltage regulation at 0. Find out the value of voltage regulation at 0.8 lagging. So voltage regulation at 0.8 power factor lagging, 0.8 power factor lagging is written as how much? So if voltage regulation represented by VR, that means VR equal to epsilon r cos theta 2 plus epsilon x sin theta 2. Okay. Epsilon r cos theta 2 r cos theta 2 plus epsilon x sin theta 2 cos theta 2 plus epsilon x sin theta 2. Epsilon x sin theta 2. Now put the value of resistance and reactance in per unit. Sorry. Sin theta 2 equal to 0.08 into cos theta 2, that means 0.8 into 0.8 plus 0.031. What is the value of sin theta 2? 0.6. 0.031. Means voltage regulation equal to 0.025 per unit. 0.025 in per unit. Okay. In per unit. Or you will say that 2.5 percentage. Okay. So we already find out the voltage regulation. So voltage regulation is much equal to how we can write. That means E2 minus V2 divided by E2 equal to this one. Okay. So E2 minus V2 divided by E2 equal to 0.025 to 5. So from this equation, we can find the value of V2. Since E2 is already given to you 250 volts. Okay. So from this equation, we can find E2, V2 equal to, sorry, V2 equal to 0.975 into E2. That means E2 equal to 0.975 into 250 volts equal to 250 volt. That is equal to how much? 243.75, 43.75 volt. Okay. Next, to find out the voltage regulation at 0.8 power factor leading. Voltage regulation at 0.8 power factor leading at 0.8 power factor leading. Okay. Have you remembered the formula of voltage regulation for the leading power factor? If you remember, then we have write the voltage regulation at leading power factor. That means E2 minus V2 divided by E2 equal to epsilon r cos theta 2 minus epsilon x sin theta. Okay. In place of positive, we put here negative sign. Okay. In previous equation. So just write here voltage regulation that is represented by VR equal to epsilon r cos theta 2 plus minus epsilon x sin theta 2. Epsilon r cos theta 2 minus epsilon x sin theta 2. Cos theta 2 minus epsilon x sin theta 2 minus epsilon x sin theta 2 Now just put here the value of one. So E2 minus V2 what we can write for the voltage regulation, that means E2 minus V2 divided by E2. Okay. E2 equal to 0.02, 0.008, 0.008 into 0.8 minus 0.031 into 0.06. So sin theta 2 is your 0.06. Just multiply by 0.6. Okay. That means it's equal to how much? This value you may be right here 0.008 into 0.8, so 0.0064 minus 0.031 into 0.6, that means 0.0186. So 0.0064 minus 0.0186 to 0.00122. Okay. So minus in per unit. Okay. In per unit. Per unit right here minus 1.2%. Okay. So in the second line, you may be right here E2 minus V2 E2 equal to minus 0.01 to E2. So just wait a minute. So E2 minus V2 equal to right here E2 minus E2 equal to minus 0.01 to E2. So maybe right here that means E2 equal to 1.002. V2 equal to 1.01 to 2 into E2. Okay. So put here the value of E2 so that you will get the value of secondary terminal voltage. That means V2 equal to 1.0122 into 250 volt into 250 volt. Okay, so that is equal to how much? 253.05 volt. Two hundred 53.05 volt. Okay. So in this way you can solve some problem and practice based on the different parameters configuration problem. Okay. So you will find out voltage regulation, efficiency, and condition of maximum efficiency in one problem. Okay. So you just try to based on your concentration on the basic formula. Okay. Whatever the voltage regulation for the lagging power factor, leading power factor. So it always keep in your mind. That means voltage regulation at lagging power factor is equal to E2 minus B2 divided by E2 minus B2 divided by E2 equal to per unit resistance cos theta 2 plus per unit decay reactance sin theta 2. Okay. Same formula is for leading power factor, but instead of negative side, instead of positive, that means epsilon r cos theta 2 minus epsilon x sin theta 2. You know? So similarly, just put the value of epsilon r and epsilon x, that means per unit resistance and per unit decay reactance, and then you solve some problem based on this one. Okay, so this way you can practice more problem, so you are able to solve any problem more frequently. Okay, various type of problem given in the textbook or something like PSBIMRA, or maybe you find out in another textbook. So you go and practice, or okay, practice and just remember all the basic formula in your mind. Okay. So just we stop here, and in the next class we will discuss another things.